Okay, this question is from Thermodynamics, and it says that during a reversible adiabatic expansion, a gas obeys this relationship, yeah, between temperature, I kind of cut the temperature and volume, and there's some K, which is a constant. Now, this gas must be, the question says, monatomic, diatomic, polyatomic, or none of these. Now, this is something very interesting, right? Because you have a reversible adiabatic expansion, and then you're talking about the atomicity of a gas. How on earth are both of these related? Well, let's write down what we know. For a reversible adiabatic process, a thermodynamic process, you know that PV bar gamma is a constant. Now, this works only because this is a reversible process. For an irreversible process, this doesn't hold good. Yeah, be careful about this. Now, in this case, we're lucky because gamma is a relationship between Cp and Cv. And both of these are a function of the degree of freedom F. Okay. Now, this degrees of freedom F they would be different for each of these gases. Yeah. And that's how we can figure out if, well, the gas is monatomic, diatomic, polyatomic, or maybe something else altogether. All right. So that's how we're going to solve this question. We're going to have to find out the value of gamma from this relationship and then get F and then figure out whether the atomicity of the gas. That's what we're going to do. So let's get started right away. All right, so the stuff I said above, just writing it down, reversible adiabatic expansion, you have PV power gamma, which is constant. Since this is an ideal gas, irrespective of what the process is, it's still an ideal gas, is what we assume, which means that this is valid. The ideal gas law is valid. Out of these, N and R are constants. Okay, number of moles doesn't change, R doesn't change. So I can write P as T by V. Now, this is maybe another constant. Yeah, maybe not necessarily the same constant, maybe constant dash, yeah, or something like that, double dash. So here I can write this as V par gamma minus 1 into T is equal to constant. I can also take that gamma minus 1 to the other side. I can say that Vt par gamma 1 by gamma minus 1 is equal to some other constant. Okay. So although I've written constant everywhere, they could be different constants. The main thing is that they are constants. All right. From here, we get gamma Cv by Cv. Cv is specifically equal to f by 2. I told you that this is a function of f. This is what I meant. And then Cp minus Cv is r. Oh, there's an r over here. F by 2 times r. Okay, this is what Cv is equal to. So sure, they're related to r. They're also related to degrees of freedom. So we have our work cut out for us. Let's go ahead and solve this question. Now, here v square t power 5 is constant, taking root everywhere, you get this expression. From here, you compare it with this, and then you get 1 by gamma minus 1 equals 5 by 2. On interchanging stuff, you get gamma equals 7 by 5. What this means is that gamma, which is equal to Cp by Cv, would now be equal to 7 by 2r divided by 5 by 2r. You know what this means right away, that the number of degrees of freedom is simply 5. Okay. Again, there's R over here. Yeah, F. So yeah, this is the general idea, right? So that's it. This implies that the gas is diatomic. How do I know this? A bit of theory, a bit of a background. You need to know that for a monatomic gas, this has 3 degrees of freedom and the X, Y, and Z axis. Okay. And if there's a diatomic gas, you have these 3, I'm just going to write that in bracket, these 3 plus 2 rotational degrees of freedom. That's what the words T and R mean. T is translation, R is rotation. There's no rotation here. So, which basically means that if there's a diatomic gas, it can rotate this way or that way, or some sort of a combination, a mix of both of these. That's what this means. There's also a vibrational degree of freedom, which means that the gas molecules can vibrate this way. But I did not write it down because at room temperature, you don't really consider this. Okay. So usually for all practical purposes, 5 means diatomic gas, and that is our answer right here.